So over the next two chapters, we're going to talk quite a bit about phase diagrams, and right now we're just going to talk about one component phase diagrams. So we'll start with a really simple one. You've seen this one before. A phase diagram just tells you what phases are present under a particular set of conditions. So we could have those conditions be pressure and temperature. So if we look at the phase diagram for carbon dioxide, we can see that if we go to low pressures or high temperatures, we end up with gas. If we go to higher pressures, we can get liquid. And if we go to really high pressures or low temperatures, we can get solid. So some features to point out on this are that this line just keeps going here. This one goes over here. But this line stops. Okay, this is a critical point. And so what is a critical point? We mentioned the critical point before when we looked at condensing gases, right? This is where there's basically a termination of this line above this temperature, which we'll call the critical temperature, Tc, and above this pressure, which we'll call Pc. We don't have any kind of distinguishing between liquid and gas. So if we were to take a container with liquid and gas in equilibrium and increase the temperature along this line, at this point the meniscus between liquid and gas would disappear. And the reason we can have critical points is that liquid and gas are both disordered fluids, right? The only difference between them is that gas is low density and liquid is high density. But as we go along this line, what happens is the gas, because it's compressible, has its density go up more as the pressure increases, while the liquid's density doesn't go up very much at all. And at the critical point, their densities become identical, and hence they become identical. They become one liquid. An important thing to realize is that if I take a gas and compress it isothermally, I'm going to have a phase transition right here, right? I'm going to condense the gas. On the other hand, if I take that same gas and heat it up at constant pressure, and then increase the pressure at constant temperature, and then decrease the temperature at constant pressure. So I do that. I will never go through a phase transition. In fact, nothing is going to be observable as I go from here to here to here. So you can go from a liquid to a gas without ever going through a phase transition. Your properties just vary continuously on this path. If we are above the critical temperature and above the critical pressure, we call this material out here supercritical fluid. Supercritical fluid, because we really shouldn't call it a liquid or a gas. There's nothing magic about supercritical fluid. It doesn't have any kind of special properties. So you shouldn't expect that as you take that gas and get it above the critical temperature or above the critical pressure that anything special happens. It just means that we can go from one to the other without going through a phase transition. Okay, enough about the critical point. There's another point here of interest, the triple point. And what's interesting about the triple point? Well, I've got all three phases, solid, liquid, and gas in equilibrium. And the key word here is, or key phrase, is in equilibrium. If I take a glass of ice water, I've got solid ice, solid water, I've got liquid water, and there's water vapor in the air. So all three phases are present, but they're not at equilibrium. It's not a sealed system. The water is evaporating. If I have a system where, and there's other phases present too, if I took a system like this where I had my glass of ice water, so here's my ice cubes floating in my ice water, and I put it under some sort of bell jar, and I sealed that. I sealed that with maybe vacuum grease, and I pumped this out so there's a vacuum. We know that pretty soon there'd be an equilibrium established between water vapor up here and liquid water and the solid water here. And under those conditions, if all three phases were left when it reached equilibrium, I'd be at the triple point. I'd be here. And notice it's a fixed point. There's a fixed temperature and pressure that's at the triple point. So these are often used as sort of reference points, because for a pure system, there's only one temperature and pressure where that will happen. We'll have these three phases in equilibrium. Let's go on to another phase diagram. This time I'll sketch out a phase diagram for sulfur. So we've got temperature and pressure, and it's going to start sort of looking kind of the same. And these are only schematic. I'm not trying to give any kind of accuracy to this. The point I'm making here is that when we look at the sulfur phase diagram, you can see you've still got liquid, you've still got gas, you've still got solid, but what's this? Well, there's two different solids. I'll just call them S1 and S2, and they're just different crystal structures of solid sulfur. So these are, because it's an element, we'd say they're different allotropes of sulfur. The S1 is rhombic and the S2 is a monoclinic crystal. The important thing is that there's more than one solid that's possible. And that means we still have a critical point out here. But now we've got sort of a traditional triple point here. Three phases are present. But we've got another triple point over here. Not the triple point, not the sort of classical triple point of solid, liquid, and gas, but one that's solid 1, solid 2, and gas. So we have three phases in equilibrium, but none of, not water. We have another triple point over here. Okay, so a triple point really is just when you have three phases in equilibrium for a pure substance. If people refer to the triple point specifically, they're talking about the one that involves liquid and gas. Okay, so that's the sulfur phase diagram. Let's do one more. And this is one where you've probably seen at least part of this phase diagram before. Okay, you might already know, just by looking at that much of it, which substance I'm talking about. This is a substance where the slope here is negative. So if I increase the pressure on this solid at constant temperature, I can melt it. All right, so you probably guessed this is water. Water is not the only substance that does this, but it's one of the only common ones that does this. Okay, so first of all, negative slope is something I wanted to point out. Same thing, we got a critical point, we got a triple point. Now this is stuff you've all seen before. What you might not have seen before is this. But there are other crystal phases of ice. And there's a diagram in Atkins. I'll just do the first couple phases. This is called ice 1. It's the kind of ice that we have in ice cubes. But if we go to really high pressures, we can form ice 3, ice 2, and if we go to really high pressures, off the scale of this drawing, there's ice 4, there's ice 6, so there's more crystal structures that form. Okay, and in fact, if we go to high enough pressures, there's actually a form of ice that's stable at room temperature, but it's not stable unless you have incredibly high pressures. Okay, so that's it for water. I want to point out you need to know the names for all the different transitions. So we could have vaporizing, or we could have condensing, we could have subliming, we could have deposition. That's that one. So you need to know, and of course, melting and freezing. Those are all important things to know. Oh, there's one more thing you should know, and I'll go ahead and do a new drawing on here. Is that on any one of these phase diagrams, and we'll just go back to, we'll go back to water. Let's clean it up a little bit. Is that if this is 1 atmosphere here, then we can just draw a little dotted line across here, and let me just annotate this again, solid, liquid, and gas, that the normal melting point we can see is right there, and the normal boiling point we can see is right there, where it crosses 1 atmosphere. Those are the normal melting and boiling points. If we were going to say the standard boiling point, that would be a little tiny bit different, because that would be down here at 1 bar, which is, remember, just 1% smaller than 1 atmosphere. So the normal boiling point up here, the standard boiling point down here. Not that much difference. The the standard boiling point for water is 99.7 instead of 100 degrees C, so pretty similar. You can get all that information just by looking at a phase diagram. Later on in this chapter, not in the screencast, but a few days from now, we're going to actually come up with a theory that's going to allow us to calculate these lines from theory. In other words, we'll be able to construct phase diagrams from theory. Or alternatively, we'll be able to look at phase diagrams and extract information about the entropy and density of systems just by looking at the lines. We'll be able to calculate numerical information, but that's going to have to wait for another day.